Okay, on to capacitors. Now, I want to just go through the basics of a capacitor. I've got a capacitor circuit here which has got some kind of cell or battery, and it's connected to two parallel metal plates. And ultimately, that's just what a capacitor is. Now, generally speaking, to make them actually work, what happens is some kind of insulator is put in the middle, so they can't possibly touch. And then they're kind of rolled up in such a way that you can have a lot of surface area of your two plates in a sort of cylindrical device or a kind of disc-shaped device. So they might be folded or rolled. But that's not really of a concern to us. Now, the way things are actually set out with capacitors is a little bit awkward, okay? And I want to just go through the equation. Now, the whole point of a capacitor is, in fact, let me just go through the general way it works first before I do that, is when you close the switch, so I've got a switch here, if I close the switch and my circuit is complete, then essentially, I've got the positive side of a cell here and the negative side of a cell there. Ultimately, electrons are drawn off this side of this plate and pushed through the cell and are moved onto this side. So electrons are pushed by the cell round the circuit, which builds up extra electrons on this plate over time. And if there's no resistance in the circuit, this is going to be very rapid. Now, once we've removed electrons from this plate and put them around on the other plate, we of course have now generated the absence of electrons, which we observe as positive charge on the opposite plate. And we have now charged our capacitor. Now, once a little bit of charge has moved around, these negative charges have a slightly repulsive effect on electrons being pushed around, which means that the next set of electrons that come around are going to come around a little bit more slowly. And what happens is this, so that's going to be a little bit slower. And then, of course, I'm starting to build up an even bigger negative charge, which, of course, impedes. So we get to a point where the negative charge and the positive charge on these plates, which is so great that no more current can flow. And at that point, if we measure the voltage across the plates, okay, so when it's fully charged, we could measure the voltage, which I would call VC, the voltage across the capacitor, and that would be eventually equal the voltage across the supply. So what happens is we started off with no voltage across the capacitor, and it slowly builds up until the voltage across the capacitor equals the voltage on the supply. And if you've got very little resistance in the circuit, that will happen quickly. That would be called charging the capacitor. Okay, so you can charge a capacitor and the amount of charge you can store on it. Now, this equation clearly is very important, but also it's got an opportunity to try and confuse you. Because, remember Q we're using for charge. So charge equals, and the C, that is our capacitance, which is really the amount, you could think of it as the amount of charge you can store when there's only 1 volt across the capacitor. So the charge you can store is the capacitance times the voltage across the capacitor. And of course, the units introduces another area for possible confusion, because charge is measured in coulombs. So you know that we use a capital C. So bizarrely, on this side of the equation, in our equation, we've got Q equals CV, but the units of Q are coulombs. Okay, so you've got to watch out for the bit of potential confusion with when are you talking about the unit of charge and when are you talking about the capacitance of the device, which is measured in farads. Farad. So that's going to be in farads, and of course our voltage will be measured in volts. And all these are named after different people: Mr. Coulomb, Mr. Farad, and Mr. Alessandro Volta. Okay, so that's that. Now, let's get on with actually charging a capacitor. Why do we charge it? What does it do? and what we'll come to later. So, charging the capacitor. Now, the important thing, I've got a circuit here now which I forgot to include the switch. You've got to have a switch in a capacitor circuit, otherwise it's going to just go off and charge itself without permission, which would be truly shocking. And so, just checking that I've got everything where it should be on the page. There we go, that's better, isn't it? Okay. So, now, if I close the switch, at that point, I've got my supply voltage across the battery. So I've got that voltage. I've then got two components in series. So I've got voltage across the resistor and voltage across the capacitor. Now, remember, we should all be comfortable with the idea that these two voltages must always add up to that. Now, at the instant when I close the switch, we have not had any time to transfer charge onto the plates. So VC is 0. Okay, at that instant, the VC is 0, time 0. Okay. Now, at that instant, really, that's not having any effect on the circuit at that instant. So we've just got a circuit where we've got voltage across this resistor, which is the full supply voltage. So, I will immediately have some current flowing. And maybe I should be measuring current up here. So actually, I need to measure my current. What's the current going round? So, at that instant over here, I can say, well, the current, the I will be given by the supply voltage divided by the resistance. Now, let's just put some numbers in. Let's call this a 12 volt supply. Let's call this a 24 ohm resistor. So I've got 12 volts over 24. So I've got half an ampere. So, and this value could go in on my graph here and say I'm going to start off with a current of 0.5 amps. Now, as time goes on, what happens is voltage is going to build up on the plate, which of course, so in this case, the way I've got this set up, negative charge is going to flow around, this bottom plate is going to become negatively charged, this top plate is going to become positively charged, and as a result, the voltage will grow on the capacitor, and as it grows, because these two voltages have to add up to that, then of course there's less voltage across the resistor. And if there's less voltage across the resistor, there is less current flowing. So if this voltage is reduced here, then of course that makes this a smaller and smaller and smaller fraction. So let's look at drawing on the graph. So the voltage across my resistor is going to slowly decay over time. Okay, until it comes down to 0. Now, let's say for the sake of argument that I've got my time axis here. All these axes are going to be time. And I'm going to try and have them as the same time. So I'm going to have 1, 2, 3, 4, 5, 6. So if the voltage across the resistor has come to 0 at 5.5 seconds, then the voltage across the capacitor must equal the supply voltage. So 1, 2, 3, 4, 5.5, somewhere up there. Okay. And another thing to consider is that the voltage across the resistor gives us the current. So if the current, if the voltage gets to 0 at 5 seconds, then presumably the current must too. So it's important that you can understand and, if necessary, reproduce a sort of standard graph. Oh, I can't believe it. I've done that in just such a bad way because I'm annoyed with myself now. Because clearly, all the graphs are curved and there's exponential functions involved in doing these. And you don't have to learn about the exponential functions. But and we don't have to deal with the maths of the exponential functions, where one of this current might equal some initial current, and then you do e to the minus a constant. It would be something like that. You'd have some exponential function for finding out the current at any particular time, which you could do, but not at higher. So we don't have to deal with these exponential functions, but these are definitely curves. So I was annoyed that my green line started looking like a straight line, because clearly this should be an exponential function. It should be curved. Now, that is charging then. So notice, charging, the voltage across the resistor decreases, the voltage across the capacitor increases, and the current flowing is initially high, and it decreases, and it is exactly the same time scale for its decrease as the voltage across the resistor. Okay, moving on quickly to discharge. Now, I made a mess with my discharge circuit, so I'm going to just quickly take you through two discharge circuit options. Okay, number one being, this is the same circuit, so I've tried to just copy that circuit across, copy it to there, and say, okay, what's going to happen if I now introduce some different switches and a lamp over here? Now, the lamp would, I don't really need the switch at the bottom. I don't really want that. Okay, so I'm going to just cheat that. Now, I would connect up a wire here, like this, to actually have my circuit charging. So I would charge it. I'd have some kind of two-way switch, which can be in position A and position B. I charge my capacitor, and then I adjust the switch, and to discharge it, I would connect it to my discharge circuit. Now here I've got a discharge circuit with a lamp, and it's very easy to do this. It's a very easy practical thing for us to do at school. So what would happen now is we can essentially completely ignore the charging side of a circuit and say, here we've got a new circuit now. The charged capacitor is going to be the source of voltage in this circuit. So it is going to provide the charge in the same way that a battery would in a circuit. And charge is going to flow off the capacitor, and it's going to flow through the resistor. Now, because we've now got a second resistance in the circuit in series, we're probably going to have less current than before. So we'd have to do the same thing and say, oh, the size of the current, that's going to be, we're just going to use our Ohm's law the other way. But in this case, we'd be using VC over whatever the total resistance was. So we'd be using our, I'd have to, let's say we said that was 24 ohms before. If that's 24 ohms, and let's say this is 6 ohms, I'd then be saying, well, I charged that up to 12 before, and I'd now have 30 ohms. So I'm going to have a fairly small current. 30. Okay. And so 12 over 30. So I should have done that in my head really, shouldn't I? 0.4 amperes. So I've got a little bit less current because I've got a bit more resistance in my circuit. And one thing to consider is, before I had current that was flowing that way through the, I had current that was flowing from the cell through the capacitor, through the resistor this way. But now, this is my source of voltage, and current is actually flowing the other way. So because current is flowing the other way, I really should express this as going to minus 0.4 amps. And with a slightly increased resistance, it would actually take a little bit longer. So if before, I'm not going to bore you with getting into those exponential functions and the value of the time constant RC and various other bits and pieces. But I would suggest that now, because it will still have a similar exponential decay curve, but now it's going to take longer to get to the axis because the resistance is greater. So let me just get rid of that. So now I deliberately said, in terms of capacitors then, 3 graphs. So we've got voltage across the resistor, voltage across the capacitor, and the current for charging. Now for discharging, we would have this This would be our current graph.